Anyway, so let's go over that. And again, feel free to watch the recording and go through logic on your own one more time, say before tomorrow's quiz, or just take a picture so you have the answers, then you can review them. Now, starting from the leading coefficient. So the test that we use the leading coefficient to figure out the end behavior tells us to just focus on what's going on the far left, right, and the far right, and please do not worry about, do not worry about what's in the middle, right? So the end behavior of this graph reminds us a cubic function. But it is a inverted, right? So this goes like a negative x cubed. And therefore, just by comparing the easy cases, you see that, oh, that looks like a negative leading coefficient. That's why the graph rises to the left and falls to the right. Okay. You guys all get that, right? The negative leading coefficient. And A sub n generically represents the leading coefficient. Now, when it comes to zeros, I think that it's obvious that there are 3 zeros. Let me just get rid of those. Well, there are 3 x-intercepts, right? Therefore, there are 3 zeros. Now, how do we tell that when the zeros have either odd multiplicity, even multiplicity? Well, looking at their behavior when the graph get close, right, to the intercepts. If you're looking at a graph that ends up being crossing the x-axis, right, when x is equal to b, that's a odd, right, multiplicity for that zero. And if the graph touches the axis and turns around, like at A and C, so you're looking at the zeros with even multiplicity. Therefore, there is 1, right, 0 with odd multiplicity, and 2 with even multiplicities. Okay. But letter D, I would like to hear what you guys think about letter D. The lowest possible degree of a polynomial function like that. Check. Say it again. Is there a way to connect question like that to something that we mentioned yesterday? What did we say? Anything about the degree of a polynomial and something about a graph? Emmanuel? The number of times the graph touches the x-axis, that's the number of zeros, right? What's the relation between the number of zeros and the degrees? Okay, now n minus 1, n is the degree of a polynomial, right? N minus 1 getting you the number of turning points, not the zeros. You guys remember that? So, but we went backwards, right? So yesterday I said for a degree n polynomial, there should be at most n minus 1 turning points. But now you're looking at 4 turning points. That means the degree must be at least 5. See that? So again, think through the logic when you get a chance, right? So the lowest degree is 5. But here's a follow-up question. Since the degree has to be at least 5, can it be 6? Or in this case, for the graph that you see over there with this kind of a end behavior, right? And we have a even degree polynomial with a leading coefficient that's negative. Rosalie? Why not? In what way? A even degree polynomial, right? I would say instead of looking at like we did x cubed. So why don't you remind yourself x squared? But with a leading coefficient negative, what kind of parabola, what kind of end behavior of a even polynomial should you expect? It goes down, right, in both directions. Therefore, that doesn't match what we have over here. That means it has to be odd. And based on the number of turning points, we know that has to be at least 5, but the degree has to be odd. Okay, does it make sense? Okay. All right. But the last one, I don't know if anyone has already came up with a polynomial function, right? Or if it could be as explicit as you can be. If you don't mind to share with us, we can test it to see, right? Because now we know almost everything we need to know about the graph. Let's see what kind of function will show you a shape of graph like that. If you haven't got a chance to write down some expressions, do it now. And if no one want to propose, then I'll propose one so you guys can check for me to see if the function does have a graph. Looks just like the one I provided you. And ABC are just constants, right? If you don't like them to be that general, you can think about any positive constants you like, right? It's just that unless we get serious about those constants, then you need to tell that B is greater than A, C is greater than B, right? Like 1, 2, 3. At this point, whether you keep the ABC in the polynomial functions or you try to use some constants, it's fine. Okay. Anyone have a function for us to maybe take a look? No? All right. Well, let me propose one so you guys can check, and more importantly, tell me why or why not the graph matches the one I proposed. Oops. All right. That's what I think that the g of x might look like. If you think that it works out, raise a hand. Okay, maybe 2 of you. Oh, 3. So what about the rest of the class? It doesn't work? Now, if you think that doesn't work, can anyone tell us that what part of the function that doesn't match what you see on the graph? Any thoughts? Roseanne, go ahead.
Is that supposed to be there?
Yeah, I put it on, on purpose. Well, that's a good question. Now, if you don't like it, let's forget about that. All right. So let's say it's just -1/5 times x minus a squared times x minus b times x minus c squared. Will that work out when it comes to the end behavior, the multiplicities of the zeros, or however many zeros we're supposed to have? First off, I mean, obviously, there's a leading coefficient, right, which is negative, right? Do you see that the three factors that I, kept, x minus a, minus b, minus c, does represent the three zeros, right? And the reason why I'm having the power for the first factor and third factor to be 2 is because I want a even multiplicity at the two zeros there, right? And also, if you want, you can take a to be 1, b to be 3, c to be b to be 2, right? C to be 3, and maybe plot it. You'll see that it's kind of close, right? So it turns out that it does work out, right? With or without that factor x squared plus 2. So now back to Rosen's question. Why am I putting the factor x squared plus 1 there? So I just want to have a higher degree because it doesn't hurt anything. Do you see that? Did it change the leading coefficient? No, right? Did it change the zeros? Or does it even contribute to any zeros? Yeah, Zach? Would that be rational? Oh, well, you have to have denominator to be rational. Oh, that's imaginary. So that's what I'm saying. My question was, does this factor x squared plus 1 contribute to any zeros? If it does, that means there must be a way for it to solve for x, right? So x squared is -1. There are solutions for x. It's plus or minus I. Right? You'll see that in 3,4 and 3,5. You guys know what I is? The imaginary unit, right? And therefore, if you see that radical -1, we used to have, issues with, negative radicands, but now it turns out that, you can have some weird numbers that works out. But the problem is, well, technically speaking, plus or minus I are zeros, but they're not real zeros because they're not real numbers, right? If the zeros are not real, do they show up on the x-axis? Because the x-axis has only real numbers, right? Therefore, that factor, x squared plus 1, does contribute zeros, but they're imaginary zeros. They don't show up on the number line. So you still have 3 zeros. But by having a factor like that, it does raise the power, right, or the degree of the polynomial. So now I'm not just looking at 5. I can make it 7, right, just by having a x squared. I can make it x to the 4th, right, or x to the 6th to raise the power of the polynomial to however I want. But I still want a odd power, right, odd degree for the polynomial, at least 5 degrees. Okay. Now, that's what I proposed. Does anyone at this point have maybe something that you thought was going to work out without this kind of weird factor of x squared plus 1 kind of thing? Yep. No, no, there could be anything. I said a possible polynomial function. If you go ahead and plot it with A to be 1, B to be 2, C to be 3 with negative 1/2, or 1/5, whatever it is, if the graph looks like that, it's a possible function. Because you see, I didn't give you all the details of the graph, right? Now, my AM class proposed, a function that's a bit different. So I wanted you guys to evaluate that, see if that works out. You know what? I think that the student put third power, fourth power. So, well, obviously, the student was taking the easy numbers for the three constants A, B, C, right? So A is 1, B is 2, C is 3. Now, what about G of X? Yeah, Ariel? Why not? Well, let's say if we went with degree 5, right? At least the 5 degree. Well, if you want, I can go with 7 degrees, right? But what's the degree of G of X? Degree of G of X. You get degree 2 from the first factor, x minus 1 to the second power. 3 degrees from the second part. 4 degrees from the last part. So the degrees will add up to be 9. So it's a high degree, right? So it will work out when it comes to degrees. It does have a leading coefficient that's negative, right? It does have 3 zeros. And also the first 0, the one on the very left, right? The student take that to be 1. And why is that an even multiplicity? Because the graph turns around, right? And the middle one, the graph go across it. That's why it's a odd power. And the last one is even power. So I'll say that this works out if, all you care is the trend, the end behavior, the wiggling, right? Or the zeros, okay? But I remember, I think it was probably a student in this class asking me something in a packet says, if you have a zero with higher power, with higher multiplicity, the graph get flat, right? How do you visualize? Like, what does it mean that graph gets flat? Do you see that here? If you zoom all the way in, if you just look very close, do you see that the part right around the first intercept is sort of like a flat, only for just a very small interval, right? And you can actually make it even flatter. And the best way to probably see it is, again, using some easy functions. Well, I guess that I need to. All right, so let me show you at the intercepts, how the graph going to get narrower or flatter due to the multiplicity. Now, first off, x squared, right? It has a 0 at the origin. Multiplicity is 2, therefore it bounces off. Let's do x to the 4th. Now, let me zoom in. Do you see what's happening at the intercept? All right, it gets flattened, right? But the thing is, does it touch more than one point on the x-axis? It seems it did, right? But it only touches the 0. it gets so flat because, you know, if you zoom in, you see that there's always going to be a little gap, right, between the blue curve and the x-axis, and it's only going to touch the x-axis at the 0. That means there's still 1, 0. Because, you know, if you make it worse, it gets even flatter. But again, don't get me wrong, there's still 1, 0 there. Okay, and you can have x to the third. Okay, now let me get rid of those things. So that's x to the third compared to x to the fifth. Right. So the higher the multiplicity, the more power it is, the graph gets flat. Right. That means if you plot those two graphs, the two functions, the one I proposed and the one that proposed by the student, the end behavior, the wiggling, right, even the zeros, they look the same. But the actual shape of that part when it comes closer to the 0, the student's going to have, let's say, a much flatter shape of the graph, because you see that the powers are way much higher than what I have. And you saw how obvious, you know, the that gets, right, when you have even just the third power. Okay. Now, but of course, you know, when in calculus, you do care about those details, right? But right now, if you ever use things that we have so far about plotting the polynomial functions, right, to solve word equations, right, or to just you know, deal with qualitatively speaking some inequalities, this is good enough, right? Or actually, it's getting you you know, even more information than you need. Okay. Now, any questions so far? Or are you guys able to do or function at this level in a test when it comes to an FRQ? So again, you know, it's not going to be tons of points in letter E, right? But I hope that everyone will definitely give it a try and figure it out, everything up to letter E, because do you see that it's not really as complicated as it seems, right? But there's no excuse, you know, not getting the first 4 letters, right? Even though that it wasn't really simply asking you to plot a graph, right? But you know that our students, not that I say you guys, but in general, when it comes to reading the graph and interpreting the data, might be, you know, even more challenging than you actually plotting the data, right? All right, cool. That's it for the 3.2. Right, so let's get to the 3.3. Right, so the long division. But you know, obviously, as you can see from things I get from a book, right, especially the first you know, couple pages, I'm assuming that a lot of you have learned it before. Therefore, let's try to be a bit more efficient on this. And unfortunately, this has to be, you know, on the test. Not to mention tomorrow's quiz is going to be about the 3.2 and 3.3. But I'm sure that you know how to, you know, figure it out. As long as the numbers or the complication of the polynomials are not as crazy as you saw from some of the examples. Basically, you need to know the algorithm, right? Anyway, feel free to follow along for the examples I'm going to do on OneNote. But you know, if you knew how to do it, then feel free to just give it a try in your own pace and just, you know, check the result for those problems to make sure that at least that you have the good accuracy for tomorrow's quiz and the test problem, you know, sometime next week. Okay. Anyway, so the first page of the packet is just, you know, trying to remind you what we have to do about division, right, in the old school way. And that's a algorithm that we will actually apply to dividing polynomials. We'll do the same exact way. Now, the first example I typed up, it's dividing the quadratic trinomial by a degree 1. Binomial I typed up so that you can, see how the algorithm works out when you have, polynomials. But I do want to point out that our book suggests that when it comes to, let's say here, so somewhere along the way, they suggest that you flip the sign. Right? Now, of course, it will be hard to go through those work, to show you where the sign flip happens. So I'll show you that, in a certain example. But what I can do is just point out when that flipping sign happens with a numerical example. All right, so 10, like 1010 divided by, I don't know, maybe 7. So you go by the first or the second digit, right? The first 2 digits, to make sure that 10 divided by 7 is enough, right, for you to do it. Then you go with 1 as the quotient, right? Then as you're coming back, multiplying 1 and a 7, I mean, you put the 7 down, you subtract it from the 10, right? But the book suggests that to make sure that you don't make a little sign error, it suggests that make the 7 negative. It was positive 7, right? By multiplying part of the quotient and the divisor, but make it opposite. So you end up adding the 2 lines, right? 10 and negative 7. So instead of thinking about subtraction, it's probably easier for you to track the signs, right? Well, it might not be that useful for the numerical case, but as you will see in the polynomial, it might be a bit better. But anyway, so it works out the same way, right? With or without flipping the sign if you're just doing the pure numbers. Okay, that's what they mean by flipping the sign. Okay. All right, so now let's try letter I think letter A. Let's see. Yeah, letter A on the page 3. Here we go. All right, so we're gonna put the dividend underneath this kind of an old school division symbol. -2 x to the third minus 10 x squared. In here, I'm gonna put 0 times x to the first power to hold a place, because you see that there's a missing term, right? The power goes from 3 to 2 to 1, so I'm expecting a linear term, but I don't have it. So we hold the place. Later on, you'll see that it will be a lot easier for you to track your work. Also, for me to grade your question in a test, I can probably find out your error a little bit quicker. So I had to suggest that you hold the place by adding a term with a 0 coefficient. -2x minus 4, right? That's the divisor. Right, so I'm gonna have some scratch work on the side. You don't have to. I'm just showing you what I did. So you start from the leading term of the dividend and divide it by the leading term of the divisor. So the number works out as -1, right? 2/2 with a negative sign, and the variable works out as x to the second power. And that will be only part of the quotient. And you're going to put the quotient on top of the division symbol. But make sure you put that right on top of the term that has the same power of x, just to line up everything vertically. And again, that's also something that you can do yourself a favor, so you can quickly go back and check your work if you ever notice something wrong. So now if you remember that, once you get part of a quotient, you need to multiply this with the divisor to reconstruct as much as you can from the original dividend. The first term, negative x squared times 2x, you're supposed to get negative 2x cubed, right? But according to the book, they want us to flip the sign to make it positive. So later on, you're going to add them, right, instead of subtracting. Now the second term, negative 4 times negative x squared, it will be positive 4x squared, right? But make it negative. Oops, what the? Again, later on, I'm not going to do the different colors, but you know that in the first round, just alerting you, it's the sign, right, that we keep flipping. Anyway, so now add up the two lines, right? The first two terms guaranteed to cancel. If they don't, check your work, right? There's something wrong with the quotient. All right, so you have negative 14x squared, right? If you add them up, then you're going to bring down one more term and start over. But you get your new dividend, and you still take the leading term of the new dividend and divide it by the leading term of the divisor. All right, so the number works out as negative 7, right? And the power of x will be the first power, since x squared divided by x. And you're going to line up the negative 7x with the terms vertically that will have the power of x to the first power. Okay. Now multiplying backwards, right, with the divisor, you're supposed to get positive 14x squared, right? If you flip the sign, because it was negative 14, but make an opposite. Negative 7x hits the negative 4. It's supposed to be positive 28, and it'll be negative 28, right? I know that I have to have an x because I know that in this column, all the terms has x to the first power. All right, so now again, add up, right? The first two terms cancel, so left with 0 plus negative 28, so it will be still negative 28 with an x, right? Now bring down the last term, 56, right? Do it for one more round. Again, it's always about dividing the leading term by the leading term in the divisor. All right, so you're going to get negative 14, right? X canceled. So negative 14 goes here, right? Coming back, negative 14 hits the 2x. It will be negative 28x, but flipping the sign, you get positive 28x. Negative 14 times negative 4, it will be positive 56, but make it opposite. Okay. Well, it just so happened that in this case, things canceled out. All right, so you're left with a 0. That's a 0 remainder, right? Then we say the dividend is divisible by 2x minus 4, or the divisor 2x minus 4 divides the dividend evenly. And a way to report the dividend, the division, like you probably saw from the first type of example, and you should also expect something like that in the test. It's going to show up as an option, divided by 2x minus 4, right? So that should be negative x squared minus 7x minus 14, right? Plus quotient plus remainder over divisor. I know it's silly to keep it that way, but at least that if you do have a non-trivial remainder, then it will be a lot nicer to keep it that way. Okay. All right. Does it remind you all the good memory back then? Kind of, right? Yeah. So tomorrow questions will be something like this, but you know, as you can tell, if there are multiple choices, so as you practice with this problem tonight, do whatever it takes to make sure that you get it right, and you know, make it quick. Okay. All right. Now let's try one more with more complicated dividend divisors, right? Especially, you know, have higher powers. And I think that, you know, maybe a couple of minutes will be good enough, you know, because we're looking at maybe another 3-4 minutes before the break. But I think that letter B will work out just fine, even though it seems quite complicated. Now, I will always start with the dividend in the descending order, even though that things has been scrambled for you. So I'm going to start with the highest order down to the third order or the third degree, right? Then we have negative 5x squared. What else? Oh, we're missing the first power, right? So let me add in a 0 to hold a place for, you know, x to the first power, and you have negative 4. Okay. So 3x squared minus 4. And again, just to be consistent, let's hold the place for, again, the linear term, even in the divisor. Okay. Yeah, let me highlight that so that you know that's something I suggest that you do. Then the work will be more organized. All right, so starting from the leading term, all right, so 6x to the fourth over 3x squared. So you're getting 2x squared, right? So just put 2x squared on top of the 5x squared. Just line up the powers. Now coming back, 3 times 2, get 6, right? The power has to be to the fourth power, right? Make it opposite. The second term, the coefficient has to be 0 anyway, since 0 times anything is going to be 0. But I know that the power has to be to the third, since x to the first power and the second power. Or, as you notice that the second column has to be x to the third power. Now, here, it will be negative 8, right? X squared, but make it opposite. Now, add up. You have 15 x to the third, right? This is positive 3 x squared, right? Then bring down the next term, right? And start over. 15 x to the third over 3x squared will be 5x, right? Then you put 5x here, right? To line up the power of x. Well, coming back, it will be negative 15x cubed after flipping the sign. There's no need to flip the sign for the 0, right? But the last term, negative 4 and a 5, you do get negative 20, but make it positive 20. Okay, x. Right, so go ahead and add up, right? You have 3x squared left over plus 20x. Oh, I should have a bit more space here. I just have one more term, negative 4. All right, so let's go ahead and take 3x squared over 3x squared. Again, always dividing the leading terms. You get 1 for the one here, right? Well, that's easy, right? Coming back, you get the same thing. 3x squared plus 0x minus 4, right? Now, flipping the sign, don't forget, right? Add up be left with just 20x. And we stop simply because that the new dividend has a lower degree than the divisor. This is just like you having a number and it being even smaller than the divisor, then you stop dividing, right? And that will make it a remainder. All right, so let me put the result in the standard form. All right, so whatever dividend it is, okay, divided by 3x squared minus 4. So you're looking at the quotient 2x squared plus 5x plus 1 plus the remainder 20x over the divisor x 3x squared minus 4. Okay, yeah, that's the long division algorithm, right? Hopefully that it's definitely doable, right? But of course, kind of a labor intensive, obviously. Now go ahead and take a break. I'll have the work on the screen in case you want to look into some detail of it. Okay. 10 minutes countdown.
10 minutes starting now.
Just because, like, I get that we're subtracting it, but,
Right.
like, I was confused, why isn't this negative? Like, here it's positive, but since we're multiplying 5x by the 4, then, then it would be negative.
And this is why the book, some teachers don't do that. The book says that flip every single sign. So, but you realize that instead of subtracting, like you normally do, you flip the signs, then you add it to the first row, the line, right? So this is like some people, so here's the thing, 4 minus 10, right? So it's negative 6, right? But sometimes people make errors because subtraction is not as intuitive as addition. So the person says, why don't you think about adding negative 10? That way, it's negative 10, right? So when they come together, 4 and a 4 cancel, well, 4 and negative 4 cancel, you're left with negative 6. Instead of subtracting, like going backwards. But I mean, it's not necessarily the case, for every person. So if you like that, you can even just go with whatever you get without flipping a sign and subtracting. But the problem is, let's say if I didn't flip the sign, it would have been negative 8x squared, right? Now, you need to subtract negative 8x squared from negative 5x. Would you still be getting 3x squared? You should, but you will probably make a mistake, right? Because remember that you could. So now, this is what I'm saying. Check. So let's say the second row, right? Without flipping the sign, you get 6x to the fourth plus 0x to the third minus 8x squared, right? And things on the top is 6x to the fourth plus 15x to the third minus 5x squared. So without flipping the signs, right? So now what you do is you subtract the second row from the first row, right? So I mean, you subtract them, they cancel. 15 minus 0, 15x squared. But this, I mean, so you have to, then you end up adding. So, but you know what? People forgot, right? And they thought, it's probably negative 3. then they put negative 3x squared, but that's opposite to what you're supposed to get, right? Right. So it's try to reduce the chance of making mistakes. It works out for most people. That's why this guy suggested. But you know what? If you find a different textbook, they might not even, say about it because you're gonna have to figure it out anyway, right? But I kind of see why they do that because after all, it does help me. That instead of thinking about subtracting negative a, it's adding the a. So I'll just say, well, just get positive. Right? Then adding, I'll see, oh, right away, that's positive 8 and that's negative 5, right? It has to work out as a positive 3x, right? Yeah. Do whatever you feel comfortable with, but I want to see the point of that.
Okay, yeah, that makes sense.
Mhm. Yeah, just someone triggers the camera in my front door.
Should we roll? I know he's actually hearing your you're hearing your wind. Okay. I mean, the Cheetos, man.
All right, let's get started. All right, so just want to clarify, as I was talking to a student over the break, if you don't like the part, you always have to flip the sign of every single term, right? Then instead of subtracting, you add row to the row right above it. You can do whatever you used to do, without the flipping the sign. Right? So I mean, to me, I don't see any difference. But of course, I choose to mention, like the book did, flipping the sign is, for me, I do find it a bit easier to track what we're supposed to have, right? So let's say in here, you see that those signs like negative, positive, positive, they're not what the original line is supposed to be, right? So can imagine that if instead of getting a plus, we had a negative, so it's negative 8x squared. Then you need to subtract it from negative 5x squared. If you want, you can always use the calculator, right? Type in -5 minus -8, right? I mean, I don't see anything wrong with that. Maybe that's also a pretty good strategy, right? But when doing mental math, and then for problems that you don't have the time to think through a lot of things, I would say that it's quite easy to make a mistake, right? And that's the whole point of behind and flipping a sign. But if you're comfortable with without doing the sign flip, by all means do that. Okay. Now, synthetic. And my point of view about the synthetic division is quite similar to the strategy of flipping signs. So it's like a shortcut, right? But it doesn't work out, in every single division. So it's like if, sometimes it does work out, then you are better off to use a synthetic division, since it does make the work a lot shorter, right? But of course, if you have to pick, like, do I need to memorize either the synthetic or the long division algorithm? I'll say the long division is the way to go. Right? It is long, and that's why you're at least trying to follow the algorithm and try it once or maybe a couple times in a homework or in a test. But I guess that later on, unless you have to teach it, there's no point of revisiting it. Okay. Not to mention that if you really have to get it for some reason, I think that TI-84 is probably not gonna easily figure it out unless you have the fancy model that you can maybe solve or install some kind of packages. But there's some softwares, right? Can do pretty much everything you wanted to, and the division of polynomial is something that takes no effort for the software to figure it out. Right. Anyway, but we do have to have things like that in a test, and I think that synthetic division might be a good way to check if you do understand it. In multiple choices. But here's the trade-off. You have to work with a degree 1 divisor in exactly the form x minus r, where r is a constant. If you want to follow the particular algebra or algorithm that this book provided to us, which I'm going to show you in a minute. Now, please make sure that the first degree divisor must have a trivial leading coefficient, right? It has to be 1, and that r doesn't have to be positive. But in this case, it is the one, right, the same as the example I typed up, right, on the first page. If you do it in a long way, right, this is what you're looking at, getting the remainder, -26, the quotient 3x minus 8. But if you do it in a synthetic manner, you identify r as 2, and instead of writing down so many x's, you extract the coefficient of the dividend, 3, -14, -10, put them down, right? And you put that 2, which you identify as the r, in that little box. You keep using it. And then you're going to leave some space underneath, the first row, right? Draw a line. Then you're going to start the synthetic division by just bring down the first, coefficient. So whatever that is, in this case is a 3, right? Just write the 3 there. And then you're going to have 4 spots, right? But this one, just leave it empty. 4 spots to fill it out with numbers. And the order is going up, then come down, then up and down, like a zigzag kind of a motion. And every time you go up, you will multiply the number, right, in the last row with that number in the box. So here you see that 3 times 2 gets you 6. right? So that's the first spot, right? Then as you come down, you will take negative 14 and the 6, just add them up. Okay. Going up, multiply with the number you kept in the box, right? Coming down, add up the two rows, and you get, in this case, negative 8, right? You come back up again, right? But now you're going to multiply negative 8 with that 2 to get negative 16, right? Then coming down, you add up negative 10, negative 16, you get negative 26. Okay. And the last row tells you the quotient and the remainder. The last number has to be a remainder, the remainder. And of course, these numbers, they are the coefficient of the quotient, right? But to recover what a quotient is, you need to put the x back in. The way to do that is, please remember that the divisor, the dividend starts with x to the second power, right? The divisor is degree 1. If you divide a degree 2 polynomial by a degree 1 polynomial, you should get the quotient that starts with degree 1, right? Therefore, 3 is the coefficient of x to the first power, and negative 8 will be the coefficient for x to the 0th power. That's why it's a constant. Not to mention that the last number, right, it's not going to be multiplied with x to the negative 1, and therefore it's the remainder. I mean, whether or not you like it, you just have to make sure that if you decide to do it, be careful with what number you're going to keep in the box, right? As you go up and down, when you do multiplication, right? When you add up, and pay attention to the sign errors, right? Sometimes, but I'll say it's more like a way of saving some work when you write. You see that it might have to take, some time for you to get used to if you never did that. So whether or not it's worth it, like I said, it depends, right? But I guess that if you see a question like the example we just did, is, probably worth it. Anyway, so let's see what we do when we have, more terms. And again, the terms are scrambled. And also there's some missing terms. And that's the only freedom we have for the standard division, since the divisor has to be exactly the form of x minus r. Okay. So let's start with rewriting the dividend, starting from the highest power, x to the 4th, right? Then we have 4 times x to the 3rd. Then we have, we're missing the second power. So let's put 0, right, to hold the place for the, quadratic term, plus 5x minus 6. Then we're gonna put the coefficients, right? 1, 4, 0, 5, negative 6. And what is r? So this guy is supposed to be in the form of x minus r. But now you see that r has to be negative 3, so that when you subtract it from x, you get x plus 3. So again, the sign error could be happening as early as, when you're getting, started. So put the negative 3 in a box, leave some space here, draw the line, right? Go ahead and bring down the 1. Now, when we go up to, the space here, we do 1 times negative 3, negative 3, right? Going down, it will be positive 1, right? 4 plus negative 3. And going, up again, you get negative 3 again. Adding up, negative 3. Coming back up, negative 3 times negative 3, positive 9, right? Add to be 14. Coming back up, 14 times negative 3, negative 42, add up to be negative 48. Okay. This guy is the remainder. Those coefficients are for the term starting from x to the third power down to the second, the first, right? The zeroth power, which is a constant. And the reason is pretty simple, because you start off with the fourth power, right? Dividends fourth power divided by the degree 1, you start from the third power. Okay. Again, I'm getting kind of lazy. So let me just write down the quotient x to the third plus x squared plus minus negative 3x plus 14, right? Then the remainder, negative 48 over divisor x plus 3. So whether or not you decide to put that negative sign down as a subtraction, it's up to you, as long as you know in the test that they might show options either this way or in a subtraction format. You just have to be able to understand what they're talking about. All right. Okay, so now how about you give it a try in letter D, and please do not worry about the P. Whatever variables you like, but keep tracking the missing terms and be careful with the sign errors. I think that's probably enough time for you to get it done. So I guess that you probably realized p to the fourth minus 81 could have been factored, right? Using the difference of squares, right? For 2 more rounds, then you see that p minus 3 is indeed a factor. So you should expect a 0 remainder. So now I'm gonna put down the dividend in the descending order with all the zeros, holding the place for the missing terms. P to the fourth plus 0 times p to the third plus 0 times p to the second power, 0 times p, right, minus 81. Therefore, I'm getting 1, 0, 0, 0, negative 81. Okay? And since we are subtracting 3 from the variable, so r is 3. Right? So we bring in a 1, and we start to fill out those spots. Okay? Come up, 1 times 3 is 3, right? Add up, you get 3. Come back up, you get 9, right? 3 times 3 is 9. Add up to be 9. 9 times 3 is 27. Come down, 27. 27 times 3, 81. Add up to be 0, right? And that's what we expected. So it should, the dividend is divisible, okay? But there's no need to predict that, right? So now you have a brutal way to check if, something is a factor. Anyway, so the quotient is p to the third power, right? See that dividend starts with p to the fourth. This is now the third degree plus 3p squared plus 9p plus 27, right? And that's it, since it has a 0 remainder. So now at this point, if you're wondering what's the whole point of doing the division with polynomials, did you ever wonder, is there like a more systematic way for you to factor a higher degree polynomial? Or let's say, do you know how to factor a quadratic trinomial? Or is it always factorable? Something like, let me put the things there. Well, that's a polynomial, right? Less trivial than the linear, but is that factorable? In the sense that you've been learning since maybe algebra 1 or 2. What do you think? What about this guy? Is that factorable? X squared plus 2x plus 1? Or now, sometimes I think that students are, seeing even more complicated cases better than the easy one. So if I make this -2, is it factorable? It is, right? X plus 2, x minus 1. You guys have done that before, right? So, but the question is, do you know how to factor every single quadratic trinomial? And it turns out there's a way, and you will learn it in 3.4. Okay. Also, the question will be, what if we go beyond the quadratic? The cubic power, third power, or n degree polynomial? Well, of course, it's going to take time, right? But the thing is, we need, now, if we could do that, we need a systematic way to do it one step at a time. And it turns out that this is going to help us. And it's not anything that's, fancy, just because, magically it works out. We ask the same questions all the time, maybe back in elementary school, and you just stop doing it, and that's why, that never become a problem anymore. You know that sometimes we have to worry about factors, right? and we do the number like multiplication, division, or simplification of fractions, we need to know like common factors. So if you have to figure it out whether 343 has a factor of 7, what would you do? How do you know that 343 does or does not have a factor of 3? Factor of 7. You divide it by 7 to see if you have a 0 remainder, right? Or do you get an integer? Do you see that? This is exactly the same thing. If you don't know whether this polynomial has a factor in the form of p minus 3, you divide it. If you do get a 0 remainder, that means this is a factor. Okay. That means if you want to break down the polynomials into, factors, like you can break down 343 into all the prime factors, right? And 7 is one of the prime factors, and you're expecting something very similar, like that. And the reason I mentioned, like those factors and how do we factor using the division, and it turns out that mathematicians already figured out something called the remainder theorem. They claim if a polynomial function f of x is divided by the factor x minus c, it turns out that the remainder will always be the function value if you evaluate f at x to the c. And the reason behind it is surprisingly simple. All you have to do, of course, they already told you, how to get started, right? So they said, you know what? We know if you divide the polynomial by a factor x minus c, what you should get is a polynomial as quotient plus some kind of remainder, right, over the divisor. And by the way, here, the reason why they put r as a remainder without a variable x, that means r has to be a constant. And the reason is you will have to do the division by a degree 1 divisor, right? Do you realize you will only stop the division algorithm when you're getting a new dividend, which is lower than the degree of the divisor. But the divisor has 1 degree. What kind of a new dividend you're going to have to stop at a certain round has degree lower than a degree 1? That new dividend has to be a constant. You see that? And we did that already. And well, we didn't go over that, right? Do you see that? Why do you think we stop dividing when we reach 27, 1 negative 26? Either people say, oh, you don't have anything to bring down. Yeah, that's one of the reasons. But do you see that this is a degree 0, right? Compared to the degree 1 divisor, this is not divisible anymore. And therefore, it guarantees that if you divide any polynomial by a degree 1 divisor, you will get a constant remainder. Where else can be 0, right? It depends on the actual dividend, but you must get a constant r. And as you can see that all they did was multiply across the board the divisor x plus c. So you get just f of x by itself on the left. Remember, just like a partial fraction, right? You have f of x on the left. On the right-hand side, that quotient q of x will be multiplied with x minus c, and you have a constant r by itself since the denominator got canceled. Then they decide to evaluate the function at x to the c, and thanks to this factor x minus c, this will become a 0, right? So you're left with the function value f of c, which has to be the remainder. Okay, that's what the theorem is telling you. Well, what do you think it's going to do to us? Well, you might get those kind of silly questions asking you using the remainder theorem to find out what f of 2 is. And do you see that they just wanted to realize, oh, the c is 2? That means to get what f of c is, let's go ahead and divide the function they provide us by the factor x minus c, where c is 2. So divide this guy by x minus 2. You know, I say, oh, that's easy because you can use the synthetic division, right? Like you see here in a book. Once you get to the remainder of 5, right, you conclude that f2 is 5. I hope you realize, would you actually do that? If they provide you the function f of x, all they want is f of 2. Do you know a better way to find f of 2? Ariel? Yeah, evaluate the function, right? Because that's what the function is all about, right? You feed it with input, you get an output. But you know, the whole point of using the Riemann theorem is that you see that it works. But of course, you know, this is just you know, a example that they carefully prepare for you to see the Riemann theorem works out. But of course, you know, it has, you know, some better application somewhere else. Oops. But again, you know, realistically, if you do have questions, you know, let's say tomorrow, as I'm not saying that you must have a question like that. I haven't, you know, pulled the questions yet. But at least that, you know, in a test sometime next week, for a question like that, don't feel obligated. You have to use the Riemann theorem, unless it's an FRQ. But I don't even see why we have to have an FRQ like that, since it doesn't, you know, have the students show me too much things, right? It's just evaluating the function. The students might just set up pretending to do the synthetic theorem, synthetic division. At the end, they're going to get the remainder by evaluating the function anyway. Okay. Well, there's another theorem which is pretty much rewarding the you know, remainder theorem. It's called factor theorem. It says that if you have a function, right, a polynomial, if you notice by evaluating the function at c, you get a 0 value, right? That means c is a 0. You can conclude that x minus c must be a factor of this function. But now, if you remember what they told us in the remainder theorem, what does the f of c stand for? F of c is the remainder, right? That means if you notice that the function evaluated at c is 0, that means it literally tells you there's no remainder. It's a 0 remainder, right? Therefore, x minus c must be a factor. And it works the other way around, right? If you're told that x minus c is a factor, then you can conclude that if you ever evaluate the function at c, you get 0. Okay. Now, of course, you know, the example that I typed up, and just to let you see how they could use it, at least at a slightly higher level, about solving equations. So, you know, that solving for polynomial equations could be pretty straightforward as long as the degree is not too high. Or nowadays, you can easily use the graphing utility, right? Like Desmos to find out the solution to any kind of equations, not limited to just the polynomial equations. But the standard way of doing it, or to see how powerful the factoring technologies could work out. But unfortunately, you need to know something to get started. So they say, so for some reason, we know that 3 is a 0 of this function f of x, which means that if you evaluate f of 3, it will be 0. But now according to the factor theorem, right, or like, you know, the special case of a remainder theorem, you know that this function, this polynomial must have a factor in the form of x minus 3, right? Because c is 3. But how do you check it? How do you know if you fact that out, right, will be the polynomial left over? Well, like I said, how would you know 343 has a factor of 7? And what would you get once you factor the 7, right? You do the division, right? So you do the polynomial function, and in this case, you can do this instead of division. And you figure that indeed the remainder is 0, right? Of course, that's guaranteed since we already know that 3 is going to be a 0 for the function. So now you're getting a trinomial, 2x squared plus 3x, right, minus 2, and that will be whatever that's left over if you were to take out a factor of x minus 3, and that x3 minus 3 guarantees to be a factor. So it has to work out, right? No extra term added. Now, when you get to this far, if you have to solve that equation, you realize either you can use the what do you call it? Zero product principle, right? To conclude that the first factor, x minus 3, has to be 0 to get one of the solutions. Now for this guy, if you have to set it to 0, or if you want to factor it now, either way, there's always going to be a way for you to solve a quadratic equation. And you might not see the whole point of this because after all, it's only the third degree polynomial equation, right? But we did something that we probably couldn't do back then, is to downgrade a higher order polynomial equation into the order of equation that we can deal with, right? For sure, because whenever you have a quadratic equation, everyone knows the worst case scenario is to use the quadratic formula to find a solution. But you have to get to a quadratic equation before you can do that. But by taking out a factor x minus 3, then you're allowed to have a quadratic, equation to focus on. Okay. Now, here's something that I want to show you, because tomorrow we have only 30 minutes, I guess 30 or even 35 minutes, since I have to have a 10 to 15 minutes, for the quiz. So please take a look at, I'll show you where it is. Page 2 on, well, you know what, let's say which one is this page. Yeah, page 2 of the packet 3.4. Right, because if you're not too busy tonight, I hope that at least you're gonna read the first page, so then there's something called the rational zero theorem that's gonna help you to do some educated guess of the zeros. But at this point, practically speaking, if we're trying to find zeros of polynomial functions, and we're given a polynomial equation like that. Yeah. You understand that by finding zeros, they're simply asking you to solve an equation, right? Just by setting the function to 0. So the question becomes, is there a way you can solve a cubic equation without graphing it? You will see that it's not about graphing, because you can always graph and find out what the zeros are. But did we just do that? But what's missing from this problem compared to the one you just solved from 3.3? They didn't tell us one solution to start with, right? That means unless I tell you that solution, or you figure out a way to get it. But the thing is, you cannot graph it. Well, there are infinite numbers out there, right? Are you going to keep trying? Say, okay, x be 1 or 1.5 or some weird numbers? Well, as you will read the first page, you will see that there is a way to guess the nice roots, nice solutions for a polynomial equation. And all you have to do is to take the constant of that polynomial function and write down all its factors. Don't have to be prime factors. However many factors you can have. So now, does it make sense that the number 6 has factors 1, 2, 3, and a 6? You guys agree, right? But what about the positive and negative 1? Well, positive 1 is a factor, right? Is negative 1 a factor of 6? Technically speaking, yes, right? Is negative 2, negative 3, negative 6, not to mention negative 6, right? Do you see that many factors, plus minus 1, plus minus 2, plus minus 3, plus minus 6, they are all the factors, all possible factors of 6, negative 6, right? So you're going to divide all possible factors of the constant term in a polynomial by all possible factors of the leading coefficient. In this case, you see that the leading coefficient is 1, therefore there's only 2 possible factors, either 1 or negative 1. But how many possible results you're going to get by dividing that many factors by either 1 or negative 1? There are a lot. But at least that you have a list of the solutions you can check, and not every possibility is going to be a solution. But if you were to get a rational, which means it's an integer or fractional solution, it has to be one of those possibilities. That means you don't need anyone to provide you a nice solution to start. You can always guess, right? But still, do you see that there are 8 solutions, right? So how would I know, let's say 1 will be a solution of the original equation? Or how would I know 1, it will be a 0 for the function? And guess what the book's going to say? Do the division. Do the single-standard division or the long division to figure it out. If you divide the polynomial by, let's say, a factor of, divide this guy by a factor of x minus 1. Why would you do that? They do it to check if 1 is a 0 of the function, like I showed you in 3.3, right? But the point is, do you see how long it takes to even do the synthetic division for all 8 possibilities? If I were you, I'll put the 1 back in the function and see if you get a 0 or not, right? Isn't it what you want? Find whether 1 satisfies that equation, or if 1 is a 0, right? Now, turns out that 1's not. 2 works out. So now you see that you have 8 possibilities, right? If you're lucky enough, you, for some reason, magically pick the 2 to start with. Then you get a hit, right? So 2 works out. Then start with the 2. So you saw we, fact out x minus 2, right? Unfortunately, by synthetic division, right? You're going to find out the remaining part of the polynomial works out as a quadratic, trinomial, and it's further factorable. Then there you go. You have 3 solutions. But what if you have a lot more to check? Even just by plugging in every single number to the function, it's going to take a long time, right? Guess what? Let's see how many you can have, right? Possibly, to check. The leading coefficient is 1, right? The constant term is 24. So can you guys tell me what are the possible factors of 24? And you always start from 1, right? Will 2 work? Of course, right? 3 and 4, 6. Yeah. And what else? 12, 24. And you know what? Plus or minus. Oh, do you guys know there's a card game called 24 or game 24? So let's say you have, let's say my son and I have 2 decks of cards. Each of you put 2 cards on the table. Then we figure out algebraically how to get 4 cards, add, subtract, multiply, and divide to get 24. Do the mental math without radical, without factorial. Just add, subtract, multiply, and divide. Now, I thought about why they came up with the game of 24. Why from, let's say, A, which stands for 1, right? King is 13. So 1 from 13, you have, the heart, the diamond, right? It doesn't matter. It's just the numbers. So why they came with the gate 24? Because you see how many factors of 24 has. It's one of the smallest number that has almost all kinds of easy factors. Therefore, it has so many possibilities to come with a way to get those 4 numbers together to make a 24. But again, I'm just saying that it's not a big surprise that 24 has that many factors. The denominator is going to be plus or minus 1, right? Because there's only 1 for the leading term. So, but there are a lot, right? Therefore, if you see how we do this problem tomorrow, it will be tedious. But the thing is, do you see that if you're always going to start from 1, which is always going to be a factor for any kind of a constant, right? And whatever leading coefficient it is, it's always going to have 1 or -1 as its factor, right? Don't you think that most problems will have some possible solutions that will be either plus or minus 1, because you're dividing 1 by 1, or plus or minus 2, or plus or minus 3, right? That means I don't need the rational zero theorem to tell me to check over 20, 30 solutions. What I always do is to check the first 6. Plus or minus 1, plus or minus 2, plus or minus 3. If that works out, great. If it doesn't, I give up. Because there's no point in doing it. And you will laugh when you see something in a packet. They say, you know what, just to speed up the process, why don't you graph this from the polynomial to find yourself a 0? The thing is, if I can graph it, why would I solve it by hand? Do you see the logic behind it is weird, because the math you're learning is from a couple hundred years ago. It's outdated. If you have the technology, but you still have to learn the right way, right? So yes, you will find something that we're trying to teach you doesn't make too much sense, or you don't see any point in doing it.